Here's my photo detection DER. As we follow the power through the positive lead, we reach two
Just kidding. Here is my third ISP of my grade 12 year, and not only the last ISP of my ACES career, but my last project. Project 3.30.4, Long ISP, Duckman Metal Detector, a project consisting of the three domains of the ICS 4U course, hardware, software, and design. The hardware section involves the Duckman metal detector circuit and the 3.7 volt lithium-ion batteries. Within the software domain lies the Duckman metal detector's code, built with an Arduino using C++. Lastly, the design component of such build involves the 3D design, acrylic design, and PCB. And, of course, the metal detector itself. The hardware portion of this project is surprisingly relatively straightforward, involving an RL low-pass filter circuit, the rotary encoder, the OLED, the 3.7 volt lithium-ion batteries, and some essential components here and there. Firstly is the RL low-pass filter, a basic circuit playing a massive role in this build. The circuit is a filter circuit composed of a resistor and an inductor. In this case, is an 100 ohm resistor, and a coil which allows low frequency signals to pass through while blocking high frequency signals. The coil within this circuit was created out of 22 gauge enameled copper wire and has a radius of 3.4 centimeters with about 30 windings. That said, the more the merrier, as it increases the detector's accuracy the more windings it has. Secondly is the rotary encoder, for which an RCC ACES rotary encoder PCB designed by Mr. Darcy was implemented. Within such PCB, a debouncing circuit is built to remove distortion from its reads. Thirdly is the 128 by 32 pixel OLED display, meaning it runs off the Nano's I2C bus. Finally is the 3.7 volt lithium-ion batteries, both of which are rechargeable and are attached to his designated 03962A lithium-ion charging board used for safety and accessibility to the batteries. Secondly is the software component of this project, in which the Duckman metal detector's code was created involving three main sections: the coil, the rotary encoder, and the OLED display. The metal detector coil works by using the RL low-pass filter circuit and measuring the delay between pulses through the coil. This delay is so significant because it is proportional to the inductance. Therefore, when the conductor is brought nearer the coil, or in this case metal, the inductance is reduced as eddy currents oppose the external magnetic field. That said, such inductance is exceptionally fragile. Therefore, just one measurement is not precise enough, so approximately 100 of which are undergone per second. Next is the rotary encoder, which was coded using the encoder's pass state. This revolves around the encoder's resting states, where pins A and B are either the same or different states, and on a change, these new states are compared to those of the past to solve for direction. Thirdly is the OLED display, used to count and track finds, allowing the user to toggle the rotary encoder, adding an additional value to the count tracker displayed within the OLED. The OLED display was coded using I2C over Adafruit's GFX library, enabling a straightforward build. The third and final component within this build was the design portion, consisting of four main parts: the PCB, 3D design, prototype build, and acrylic. Firstly is the Duckman metal detector PCB, measuring 73 by 70 millimeters, created in a black colorway. In addition to the DMD hardware explained earlier, on the PCB is an optional button, added with the idea of the possibility of a new function yet to be programmed as of today. Secondly is the 3D design, in which 5 different components were designed and manufactured: the main case, its door, the 2 PVC connectors, and the bottom acrylic holder. First is the main case, in which the rectangle-shaped design was adapted to fit the PCB on top, while also making room for the bottom components to store within the bottom, being 2 3.7 volt lithium-ion batteries, which can be charged via the barrel jack on the side. Secondly, within the case was the door, used to conceal the batteries, but when needed can be opened through friction fit. Next was the pipe connector, made up of 2 components, the first of which was mounted to the main case using more screws attached to the main case's 4 heatset inserts. Then, the addition of more heatset inserts used to connect the piece to the other connector, when merged, making up just less than a full circle. These components hold the pipe in place through the tightness of the screws. Lastly, on the 3D printing end was the acrylic holder, a rounded cylinder with a lip at the bottom used to rest the acrylic on top of and screwed into the PVC pipe's base. Thirdly was the prototype build, created using 1/2-inch PVC pipe connectors and screws, used to mount the entirety of the build. And lastly was the acrylic, made up of 3 different pieces, all of which were used to hold the coil at the bottom of the detector for looks and strength.